professor Kai, ele atua há mais de 20 anos com o mercado brasileiro. Ele é doutor em engenharia, é gerente de projetos tanto de tecnologias para aterros como instrumentalização laboratorial. Ele tem uma carreira que combina a expertise da Alemanha com a expertise em países em desenvolvimento. Isso é de bastante valor para a gente, principalmente para entender essas diferenças, tanto de questões financeiras, como climáticas, como culturais, e com isso eu entendo que vai ser bastante rica a apresentação dele.
Good morning, Brazil. It's a pleasure for me to give you here from the very cold Braunschweig at the moment to give you this lecture about MBT and landfills. So I will not speak about MBT, the technique of MBT, but the consequences of MBT which we have on the operation and construction of landfills. So as you see, my lecture will be in English as my Portuguese is very poor. So it's better to give it in English. So it's within this network between Brazil and Germany. This is different universities, and we here are a small part of this network. So let's start to have a look at landfills in total. So when you are hearing something or you are reading something about landfills, in most cases, it is a problem we have with landfills. You see these situations here all around the world. You can look at Asia, big amounts of waste here, waste directly nearby a watercourse, so river littering, for example, and also then marine littering. In Africa, the conditions of people living nearby landfills is a catastrophe, or here emissions. Or also in South America, in some parts, here these wildfires, these open fires we have on landfill, or here a lot of birds. And here it's a very strange landfill. I have just got these pictures a few days ago. It is a landfill in the desert Atacama. And on this landfill, only old clothes are deposited. It's only made for clothes, so it's terrible to build up a landfill only for these purposes. And it shows us that we have a problem with waste. So a lot of impacts are associated with waste. We have the environmental impacts, we have health impacts. So if you look here at first at the environmental impacts, air, gas emissions, the big problem of greenhouse gases. I think you have heard it also in other lectures. Then also fire, as we have seen, problems with water. I think this is a problem, a very big problem in a lot of countries, especially if we have a scarcity of water. So if we don't have enough water, and this water is polluted by landfills, for example. So especially groundwater supply sometimes is a problem. Then also contamination of soil, land, changes in vegetation, for example, or big areas are now landfills instead of areas where you can build up houses or make agriculture, and also contamination you have. On the part of health impact, so we have chemical entities, which means we have some toxic components in the waste. Then also during the process of disposal and the operation and on the long-term behavior of the waste inside of the landfill, new products are sometimes produced and they are emitted into the environment. Then we have also biological entities. We have sometimes, as we have seen, animals, birds on the landfills, pathogens, a big problem if it's not made in a good way. Then also an aesthetic impact. It's not as important as these two, but it's also a problem. Sometimes odor, litter, which is spread all around in the area of the landfill. And also it's not a very nice view to have a look at a landfill every day. And at last, we shouldn't forget, we have also here some social problems. In many countries, we have waste pickers, which are taking out some materials out of the waste on the landfill itself. So this is a big problem. If we close this landfill, these people don't have a job, so we have to think about it, how to manage it also for these people. If we are looking at the impact, then we can see that there's a certain dependence on the distance. If we have here our landfill, then nearby the landfill, we have a lot of local problems. So if we start with fire, odor, dust, then also damages to soil, to vegetation, then groundwater pollution, very nearby. We can see it very often that people living directly on the side of the landfill, they use surface water or groundwater for their purposes, and this water sometimes is polluted. We have these problems of river and marine litter also. We have pathogens, as we have seen, and this is also a big problem if the landfill in total collapse, if we have a structural failure when all the waste is moving down, for example, such a big heap of waste, and if there are people living nearby this landfill, they get a big problem. On the next scale, on the regional scale, also dust. Here now also groundwater pollution, surface water pollution, and also littering of water. And the last one, the global problem we have, greenhouse gas emissions and marine littering. So the problems are quite different. People living here nearby the landfill, they are looking more at these problems. But if you look now about at the discussion we have about landfills, we are always looking at these global problems. So for the people, the local problems are more important than the global problems. So let's have a very short look here at greenhouse gas emissions. Everybody is talking about it. I think you know this figure. In Germany, how much of the CO2 emissions are coming from waste management, and here especially from landfilling. If you look at this graph, you can see nearly 78% of the CO2 emissions coming from waste, from the waste sector, is coming from landfill. This sounds to be a very big number, but if you look at the amount, these emissions in 2020 have been nearly 9 million tons of carbon dioxide equivalents. So this is the total. But the total emissions, not only from waste, but from traffic, from construction, and so on, in Germany had been nearly 740 million tons of CO2 equivalent. And now you see it's about 1.2% only are coming from waste. And if you look at landfilling, this big amount, it's less than 1%. So it's not a lot, but we have to look at it. We have to treat also these small emissions. And the same you can also see for Brazil. Here, the official data set, it's about 4.3%. I know there's a heavy discussion in Brazil about these numbers. They are estimated to be much too low. These are the official data. It's always a little a problem. But what you have to take into account that in the last years, a lot of technical measures have been made to avoid greenhouse gas emissions from landfills. So I think Professor Jucard have shown you what has been made in the last years in Brazil, and the emissions from landfills are reduced to a big amount. There are still a lot of old dumps where we don't have such a collection system for landfill gas, but for the big landfills we have in Brazil, more or less now the problem is not solved, but it's reduced. what are we talking about? Everybody of us here living on this earth produces about 0.7 kilogram of waste every day, which means 2 billion tons. So I think in Brazil it's a little bit more, it's about 1 kilogram. And here in Germany it's even more, it's about 1.7 kilogram. So it's a lot of waste which is produced every day, and we can expect that because of population growth, worldwide growth, economic growth, so the difference between the very poor, the poor and the rich countries is diminishing, and also because of urbanization, the amount of waste in the next year will increase if we don't stop it. So here from 2 billion tons, maybe we have until 2050 about 3.4 billion tons. And the question is, where does the waste go to? Here's this data from the World Bank. It's the newest one. You see about 1/3 of the total amount of waste is going to open dump. Open dump means a place where we don't have any technical installations to avoid groundwater pollution, gas emission, and so on. So this is the poorest quality. Then about 25% are landfills, where it's a little bit better than an open dump, but not much better. Then we have controlled landfills, where we have at least a liner system at the base to reduce or to avoid groundwater pollution. And only nearly 8% of the waste is going to sanitary landfills, which are built up at the state of the art. So also with landfill gas collection and sometimes use of this landfill gas. So it's a very small part. Then we have a certain amount of recycling, a little bit of composting, incineration, more than 10%, and other techniques. But you can see out of this that about nearly 70% of the waste at the moment is going to landfills. But if you have a closer look at these numbers, you will see that there is a big difference. If we look at these countries with a high income level, so US, Canada, Central Europe, Japan, there you see we have only a small amount of this very poor landfills. Most of the case we have landfills with a high standard. We have certain amount of recycling. Recycling is much stronger, nearly 30%, and also incineration is increasing in the last years, and about 20% are now incinerated. If you look on the other side at the poor countries, it's completely different. Now you see more than 90% of the waste are going to open dump, where we don't have any control of the emission to water and the atmosphere. So in the last year, some landfills have been built. Composting is very poor. Recycling is increasing a little bit in the last years, and the rest you can forget. And you can be sure that this will not change within short time. Now, if you look at the development we have here in Europe, it took us more than 20 years in Germany to close these old landfills, to go more in the direction of incineration or the treatment of waste before disposal. And also in the EU, it's still a process since more than 20 years. It's not finished. So we try to get away from these old dumps we still have also here in Europe. But it takes a very long time. And you can be sure that in these countries, where the people have much less money than in these countries, it will take much more time. So we cannot change it from today until tomorrow. It will take a lot of time. And this is why we have to think about some techniques we can use, which are not so cost intensive, but which are showing us good results. So just a short look of the types of landfills we have for municipal solid waste, which is not treated. So the standard waste, which is collected in your city and which is brought to the landfill. So this is what we want to have, a sanitary landfill, which is a more or less uncontrolled bioreactor. So the waste is coming to the landfill and all the chemical biological processes starts and we cannot control them. They will start by their own and we have to see what is happening with leachate and the gas. So here the emplacement should be high, so we can put a lot of waste in this landfill. Then we get in short time high loaded leachate, high concentration of different parameters. So we have to purify it before we give it back to a river or to groundwater. And by this high amount of organic we have in the waste, we can also take out the gas. We should start very early with this gas collection, and this should be used for energy purposes. As we have here some problems, here it's called dry tom, which means that when the operation phase, so the phase where we put some new waste on this landfill is finished, we put here a cover on it and no more water is coming inside. So the waste is getting dry and the process stops. So this is why we call it a dry tom. So we have problems with this technique, which is standard worldwide. So we have some new developments. We have this anaerobic bioreactor landfills. It has been developed in Canada and in the US. And the difference is that they make here a leachate recirculation to intensify the gas production. So they want to produce as much gas as possible in the first 8 to 10 years, when we know that all our systems we have installed here in our landfill are working very well. So by this leachate recirculation, they know that the supply of the microorganism inside of the waste with water is much better than in this case. So the biodegradation may occur much faster. Another type of landfill we have is this flushing bioreactor. So on one hand, we produce a lot of gas by this recirculation, but in this case, we add even more water to flush out a lot of components which are not degraded, which are inside, which can be flushed out by water, maybe ammonia, and also the hard COD, this chemical oxygen demand. At a certain level, at a certain concentration, it's very difficult for the bacteria to reduce this amount of organic substances. But you can flush out these components if you add some water, yes, and also other salts. Yeah. Also here we have a little bit of experiences. It's not very easy during the phase of operation for such a landfill. So this is why we have only a few numbers of landfills which are working with this technique. And another one is then, just a moment, here we have it, this semi-aerobic bioreactor landfill. This is a landfill which has been developed in Japan more than 20 years ago. We have also some smaller landfills in Europe, especially in Italy. And here, in the beginning, when they start to put the waste in this area, they have anaerobic conditions, the same as we have in the other landfills. And after 10 years, maybe 6 to 10 years, they stop with this extraction of gas, and they blow here from the bottom, they blow air inside. So it's changing from anaerobic to aerobic conditions. So in the anaerobic conditions, they get the gas, they can use it. When they switch to aerobic condition, it will stop. The advantage is that aerobic decomposition occurs much faster. So by doing so, by injecting here air at the base, we get here aerobic conditions. The temperature inside of our landfill will increase, and the remaining gas, so the remaining methane, but also carbon dioxide, is coming to the surface where we can collect it. And also, if we inject here air inside, we get out a lot of water. So also this landfill will become dry over time. So you see, we have quite a number of different techniques to reduce the impact of landfills on the environment. So the problem we have with landfills are mostly coming from the organic waste. Food, for example, or here fruits and so on, to a certain amount, 30%, 50% of the waste may be made out of organic waste. How can we solve this problem? So I think here, this is not the solution. You can see all around the world, it shows you that the technique is not working very well, that animals are on this landfill, big animals, as you can see, and they are taking out here some of the organic. But I think this is not the solution we want to have. So how to treat waste? A very, very short look only. As we have seen here in the countries with high income, we are looking at incineration. What are the advantages? If you incinerate all the waste, you can get out energy, electricity, heat. And this is a very big advantage, that you can reduce the big masses of waste in very short time. If you look here at the mega cities in Brazil, Rio or Sao Paulo, where we have 5,000, 8,000 tons of waste every day. What to do with this big amount? And I think for these big cities, incineration might be a good solution. But on the other hand, there's always a risk of air pollution. The most important in an incineration plant is the filter system, and this filter system is very expensive. So sometimes we have some problems with this filter system. Also, the acceptance in the population is in many parts quite low because of this risk. You have really high invest costs for building up such an incineration plant. And what you also have to look at is, at the moment we are talking about a lot about climate change. We want to get out of this carbon fuels. Everybody should use renewable energy. And if you are incinerating waste, and the best, which has a high calorific value in the waste, is plastic material, so you want to have a lot of plastic inside, you get a lot also of carbon dioxide, fossil carbon dioxide. And this, it's also emitted into the atmosphere. And for the atmosphere, it doesn't matter if it's coming from a car, or maybe from your heating system, or it's coming from incineration. Here you can see typical values we have, how much carbon dioxide, fossil carbon dioxide is emitted when you incinerate waste. So we have to think about it. Also, we are discussing, especially also here in Europe, about carbon dioxide taxes. And we have taxes, for example, in Sweden here, about 150 euro per ton. And who will pay for it? As a consumer, it might be a problem. So we have to think about it in any case. And what you also have to keep in mind, also after incineration, we have some materials which are not burning. So these slags, sometimes they have high concentrations of heavy metal. What to do with these slags? Here in Europe and the US, most of these slags are going into construction, especially in road construction. But we have some other countries where this is not allowed, and we need for these slags also a landfill. And this filter dust, which is coming from the cleaning of the exhaust gas, it's highly contaminated. So here you need a landfill for hazardous waste. There are some techniques they try to use to recycle also this dust material, but it's very expensive. As we have just seen, anaerobic, where we have this energy production, this methane production, where we can get also electricity and heat out of the waste. But also here, if you look at such a plant, then you have always higher invest costs, and the quality after the treatment in such a plant is not as good that you can put the waste without any problem on a landfill. So you need the second step, this aerobic stabilization. So this is the same what you are doing in this semi-aerobic landfill, but here under controlled conditions. At first anaerobic, and then you aerate it and you degrade the remaining organic substances. Or you start from the beginning on with an aerobic technique. Here's such a system with a Gore-Tex sheet on the top to avoid emissions or to reduce emissions. And also the rainfall shouldn't come too much into this landfill, because if you have a lot of rainfall, maybe then also your landfill is getting anaerobic much faster. This also you have to take into account. But disadvantage is the treatment time is most cases much longer, and you need large areas to treat, because here the height of such a windrow is limited, and you don't get any energy out of it. But we will have a look here only at MBT. Or at first, let's have a look what is the consequence, what to do with this material. So we need, if you don't want or if you cannot use the slags for construction purposes, we need a landfill for this incineration slags. Sometimes it's mixed with fresh waste. But if you have big amounts, then it's better to build up a mono landfill only for the slags. And you will see, if you look at the leachate at the base, you will have a lot of chloride inside, which is a problem over a very long time. And also, you might have here some gas production inside because of chemical processes, not of biological process. And it's not methane, it's hydrogen. So maybe you get also here some problems in view of safety. This is for the normal slags. You need also here the space liner system on top. Usually only soil material as a top cover system is enough, and the leachate also have to be purified. If you have now the fly ashes from the filter, then you need a landfill for hazardous waste. So also after incineration, maybe you are still needing a landfill. And the same for output from MBT. Also here we need a landfill with a baseliner system. We have here, after the biological treatment, we still have some processes which occur inside of the landfill, which also produce a little amount of gas. And this gas we can purify with very simple techniques. So we don't need, for example, a system to extract it with wells and so on. We can use a passive system, but we will see it later on. So this as a kind of introduction. Let's go to the landfills. What is the difference between a landfill for fresh waste and a landfill for MBT output material? So we will have a look at these different points, a short view at the properties, which are very important for the construction and also for the operation, but also in view of the leachate emissions and the very important point of gas emissions. So this is what we know very well, the situation. Everything which is inside of your waste bin is going directly to the landfill. And if you have a look at the waste, what you can see, which is only under the aspect of looking at it, you have a lot of plastic inside. And you see there's a big difference. We have in the size, we have very large parts of waste. We have very much of these fine materials. And very often large parts is plastic, fine material is the organic. So this is what we know for a long time. And this might be a look of the waste after it has been biologically treated. So a big difference. So the color has changed to this typical brown color, which shows you that the organic material is oxidized to a certain amount. And you still have here some plastic parts inside, woods, glass, and so on, but the size is much smaller. So if we have a look of the effects of the treatment on the landfill material, so on one hand, we are reducing the mass. So if we bring 1 ton of waste to the MBT, we are removing recyclables, plastic, iron, wood, and so on. It's depending on the waste, 20 to 30%. And then the step of biodegradation, also depending on the amount of organic material inside, here 30 to 40%. In this step of treatment, not all of the organic material is degraded. There is still a certain amount remaining inside of the waste. Some substances, as wood, for example, are not degraded under the condition of MBT. And as we have seen, we have this strong reduction of material size. In the beginning, when we start with MBT, we take out the very coarse materials. If you have larger parts of concrete or battery from car and so on, we take it out. Then we make a separation of plastic material and also textiles. They are going to the sites that might be incinerated, for example. Then we have this reduction of the material size because of shredding. We are shredding all the waste before it's going to the MBT. And then also during biological degradation, we have a degradation or a reduction of the material size. And usually the material, when it is coming out from the MBT, has a size smaller, 60 millimeter. It's depending on the technique. Sometimes you have 20 millimeters, as you can see here. This very fine material, you can see only small parts of plastic inside. The next step, up to 40 millimeters, the amount of plastic and coarse parts is getting higher, and at last 60 millimeter, we have still a huge amount of plastic material. So these are the physical parameters. Then we have also the biological and chemical parameters. So these values here are from the German landfill ordinance. So if you make a biological treatment in Germany, these are the values you have to meet. The TOC, the organic carbon in the solid material, less than 3%. in view of the dry substance. Then you have to make a leaching test. You have to analyze a lot of components, heavy metals, but also the dissolved organic carbon, 300 milliliter, quite low. Then you have to look at the biological parameters. You can make a respiration test under aerobic conditions over 4 days, and a very low amount of oxygen demand is still allowed. Or you make a non-anaerobic tests over a longer time, 21 days, and in maximum 20 liter of methane and carbon dioxide are allowed to be produced. And you have here last parameter, the upper calorific value. This has nothing to do with the behavior on the landfill in view of chemical and biological parameters. So this value is only to be sure that most of the plastic has been sorted out. If you have too much plastic in the remaining material, then the value will be higher and it's not allowed to go to the landfill. And in total, we get a reduction in the production of landfill gas, and also the leachate is less loaded. Here's such a nice picture. Usually, if you look leachate from fresh waste, it's black to very dark brown. And if you have here leachate from an MBT material, so it's clear. It doesn't smell as strong, but there are enough substances inside that you shouldn't drink it. So you still have to purify it, but it's totally different here if you compare it with leachate from fresh waste. And at last, we take out more or less most of the harmful substances if we can identify them. Before we put the waste in the mechanical treatment, somebody is looking at it if there are some hazardous substances inside and take it out, so that in the end we have also lower concentration of these substances in leachate or in gas. So now we have our material and we want to place this material on a landfill. If we want to build up a new landfill only for this waste, there are a lot of criteria we have for standard landfills, and they are quite similar to what we need if we want to build up an MBT landfill. There are no such big differences. So in view of the selection of the site, you should look at the place where you want to build up your landfill. So not in regions where you have an earthquake or where you have floodings, for example. There are a lot of criteria you have to look at. You still need an entrance area, but now not the trucks which are collecting the waste are coming to your landfill, only trucks which are coming from MBT plant. So the control of this waste is quite different. It's much easier to control such a waste. You still need a baseliner system, but you have to think about if you can use lower requirements in view of the building of this system. So in Germany, we have for MBT landfill still a mineral layer, mineral sealing system, and on top a geomembrane. And we have the same baseliner system for fresh waste. And you can discuss very well why you need for MBT waste such a geomembrane, for example, or maybe also the clay liner, because the leachate has much lower concentrations. They don't have this organic fluids inside, which are very critical for the baseliner system. But you still need a drainage system, as also for fresh waste. You need also the purification of this leachate, but you have to look at the technique you want to use. It is different. You don't have this very high concentration of organic substances. Then what you have to take care is that the density of the MBT material is much higher. So if you build up a landfill, for example, 20 meters high, the load at the base is much higher if you have a MBT material 20 meter high, or you have a fresh waste 20 meter high. So this you have to consider in view of the risk of base failure, or also damages to the drainage pipes. So usually the normal system of drainage pipes is working, but you have to have a look at it. You don't need anymore a daily cover system, so it is not necessary anymore. We will see it later on. And also you need a final top cover system, but also here maybe that the requirements might be lower, because the gas emissions also are much lower. And you don't need to install shafts, drainage system for collecting the gas. This is not necessary anymore. So this is for a new landfill, but sometimes we already have an old landfill body and we want to use the site also to place there our MBT material. So here's our old landfill body, maybe on the top and on the side we build up a landfill, or here only on the side or only on the top. Here in Europe we call it landfill on landfill, because the new landfill body is in direct contact with the old landfill body. When you want to do so, you need here a system in Europe to separate your old waste from the new waste. So you need here this top cover system, and this top cover system is at the same time the base liner for the new landfill. Here the same, the top for the old or the base for the new landfill body. So this is a so-called multifunction layer system. It's not a problem to install such a system, but what you have to keep in mind when you are planning such a cover system is that here the base of the new landfill body is not the natural soil. It is the old landfill body. And maybe this landfill body has not been compacted very well, so it's quite soft. If it is quite soft here in this area, you might get settlement. Problems with settlements is always that we have differences. In some parts, maybe the settlement is 1 meter, and 2 meter on the side, it's only 50 centimeter. So these differences are always causing problems. So maybe if you have this non-uniform settlement of the old landfill body, is damaging here your cover system. So this is a big risk you always have to look at. So let me say, if you are looking in Brazil and you have an old small dump, then I think this is not a good solution, but because you can be sure that this old dump will have high settlements because it's not good, the compaction has not been good. So there you must be careful. You must have a closer look here to make some investigations about this old landfill. So this so far in view of the construction. Now let's have a look in view of the operation of the landfill. So this is what we can see very often when we have fresh waste. Here you can see the engine for distributing the waste, or you nearly cannot see it because you have a lot of birds flying around because you have a lot of food for these birds. Or here, I think it's a landfill in Brazil, typical surface. They started to place the waste in another part, and now it's an open part. You see some plants are coming out of the waste. Here they have tried to install a gas collection system. It has been destroyed because of the movement of the waste. So this is a typical situation we can see all around the world. And so this might be the look after you have made a treatment of the waste. You don't have these birds. The material is looking more homogeneous. You can place it much better. You get here a nice surface. So something completely different. Yes, and this is what we try to build up when we make a new MBT landfill. So out from these pictures, you can also see that now the engines we need for operation might be quite different. So for both landfills, fresh waste and MBT, usually for waste distribution, we use here track loaders, caterpillars or whatever. Also for MBT waste. Here you can see now not the collection trucks coming from the city, they are disposing the waste. No, it's directly from the MBT plant. So here it's an open truck because the MBT plant is nearby the landfill. If there's a longer distance between MBT plant and the landfill, you can use a closed container system to bring this waste on the landfill. It's not a problem. And then it's spread here in thin layers, and it's not compacted. It's only distributed. We know that here this compaction of such a with such a caterpillar is quite poor. So it's only for distribution. If you have a standard landfill with fresh waste, for the compaction, you should use a compactor. Here you can see such a compactor. And in the case of MBT, it doesn't make sense. What is the function of the compactor? It has a very high load. That is very nice. And with his special wheels, he is also crushing the waste. For MBT, we don't need it because we have made the crushing at the MBT plant. So this function is not necessary. And what you can see, if you make tests with such an engine with MBT material, this type of wheels is not good for the compaction because when he's driving over the surface, he's loosening here this material again by driving over it. So better use another engine, for example, such a pet foot roller, very similar but smaller, let me say, teeth here on the surface of the wheel. And what you get when he's driving over it, it's looking very nice, but this is not what we want to have. You see here a lot of these small holes on the surface. It's very well compacted, but when it's raining, all these little holes will be filled with water, and this we don't want. So we need a second step for the compaction, and we take a smooth roller with vibration or sometimes also without vibration, and then we can close all these small holes by driving over it. So in total, after 3 to 4 runs, you have a very nice density. Here you can see that the material is quite elastic. He's driving over it. When he's going to the side, here the surface is coming back. So the settlement, this temporary settlement of 1 to 2 centimeters is going back. What has happened here? You can see here such a nice wave. Here in the background, the material has been distributed, and here they started to drive over with these 2 engines. And why do we have this nice waves? It's because here in this part there has been some equipment to distribute here the waste. It has not been made only with caterpillars, but another engine has been used. It was standing here, distributed the waste to the side. So this area has been already compacted to a certain amount. and this material has been loose, and by driving over here the settlement has been higher. So you should avoid it, because then if it's raining also here you will have a lot of water on the surface. So, but this is quite normal when you start with such a new technique. In the beginning you have some problems. It's very important to identify these problems and to solve all the problems. So let's have a look at the physical behavior of our material. Here we have a comparison between fresh waste and the MBT output. At first, emplacement density. So how much waste can you put into 1 cubic meter? So here it is related to the dry substance. So not the water content is important, but only the dry substance. For fresh waste, you have values between 0.5 to 1 ton per cubic meter. And for MBT, it's quite higher, 1.5, sometimes even more. It's depending on the waste and the treatment technique. So this means that in the same volume, you can place more waste. That's important, that now you can bring much more waste on the same area if you compare it with fresh waste, because you can have a higher density. And a big difference, the optimal water content. Here for fresh waste, we don't have a value, because the waste is brought by the truck, it's unloaded, it's compacted, and nobody knows what is a good water content. Here with MBT material, it is more like a soil. And if you look at soil mechanics, you will see that there is a close relationship between the water content of the material and the achievable density. If it is too dry, you cannot compact it very well. If it is too wet, also then the compaction will be poor. And we have in between an optimal water content. And this is what we try to have also on the landfill. And as MBT is a more or less industrial process, we can also have an influence on this water content. We can tell to the owner of the MBT, please have a look at the water content of your output material and try to be in this range of water content. If the water content is too high, maybe you have to aerate it for a longer time, so it is getting drier. A consequence of this high density is that the settlement is much lower. We will have a look later on also. So about 50% of settlement we have less in the case of MBT output. And also here, the problem is not the total settlement, but the differences we have on the surface of our landfill. And as our material now is more homogeneous, we don't have this big differences in the case of MBT. If you have fresh waste, maybe on one side you have more construction waste, on the other side you have a lot of organic waste, then in the area of the organic waste the settlement will be high, and close by where you have the construction waste, settlement will be low. And if you want to place a cover system, then you get a problem with these big differences. Then some values from waste mechanic, shear strength, cohesion and tensile strength. These are parameters which are describing how you can build up your landfill, how steep is the slope you have to build it up, and also how high is the risk of failure. You see some parameters here, there is nearly no difference, only in the tensile strength, which means that here, in the case of MBT, we are sorting out most of the plastic material by, as we have seen, this upper calorific value. We have to take it out. So most of the plastic is taken out. So the tensile strength is reduced because this plastic material is able to take these tensile forces inside of our landfill body. The last one, in view of leachate, but also in view of the gas movement, is the permeability. Here the hydraulic permeability for water. You see quite high for fresh waste, and here for MBT output it is much lower, which means that also less water is flowing through our landfill. Let's have a look at some of these values more in detail. Let's start with this emplacement density. Here you can see different tests which have been made with waste, which has been treated or not treated, and which has been placed with different techniques. Let's have a look here at the red column. So this is the mass of waste which is coming directly at the disposal area. The other one is the mass when it is delivered at the MBT. So if you put this waste on the landfill and you do not compact it very well, maybe you get emplacement density, dry density of 0.56. So this is a very poor technique. So if you shred your waste, you make the material a little bit more homogeneous. You place it in thin layers so it is compacted better. So you get an increase from 0.56 to 0.67. So the density is increasing. If in the next step you make a high compaction, you shredded it much better, maybe you sieve also some parts out, you always get an increase in the density. And in the last step, if you take this waste here, put it into the MBT, the output now is going to the landfill, you get an increase of the density of 0 to 0.87. So if you compare this value with the one of the beginning, then we have an increase of about 55%, which means that we can use our landfill much longer because we can place much more waste on the same area because we compact it much better. And if you now look at the green column, this is the mass at delivery at the MBT plant. Here the difference is occurring because now we make also recycling. We take out the glass, we take out plastic and so on. Then we are able to compact it even better. And if you compare it with the mass of the ton we are delivering at the MBT, then we have an increase of about 80%. So the lifespan of the landfill is much longer. And that is very important also in view of the costs. The next point, in view of the emplacement density, as we have seen, the settlement. You can see when we put the waste, the MBT output on the landfill, we compact it, we get a very fast settlement. But when it's built up slowly over several years, then most of the settlement has already occurred. When it's finished, we don't have much settlement on the long term. This is very important. So this so-called secondary settlement is very low, 2.5 to 3%, because we don't have these strong biological processes. In fresh waste, we have a lot of biological processes, and therefore we have also this strong settlement. creep means this very slow settlement because of the huge amount of plastic, for example. And we have taken it out, so the problem is not occurring anymore. So, as we have said before, on the long term, we don't expect these large differences. Now here you can see such a cut in a landfill. So it's not looking only nice over the surface, but also here in the cut you see this material. You don't see here big areas where you have a lot of pores. If you make the same with fresh waste, you will see a lot of holes here in this wall. So this means also for the end of the landfill, when all the waste has been placed, that we can place this surface sealing system much earlier than in the case of fresh waste. If you put fresh waste on the landfill, you have to wait until the main settlements of the waste have occurred. And this is happening much faster in the case of MBT. The next effect we have just seen is hydraulic behavior. Hydraulic behavior is closely connected to the amount of leachate we are collecting at the base, and we have to purify in our treatment plant. Because of this high density, the infiltration rate, which means this is the amount of water which can flow into the waste, and the high permeability, that's the movement of the waste inside. So there's a little difference between these two parameters, but in both cases they are strongly reduced. The consequence is, as the hydraulic conductivity is low, that not all water, when we have a heavy rain, can flow into the waste. So we get surface runoff. Also, water which is running over the surface is not going through our waste. So we have less leachate at the landfill base. That's a positive effect. But if we have this small permeability and we have a certain amount of water and we place the next layer of waste on it, maybe we get problems with pore water pressure. So we have to look, in any case, at the slope stability. So if we make calculations of the landfill stability, we always have to look at pore water pressure. And as this material has a high density, it has had a small material size, also the evaporation rate is high. If you look at the normal surface of fresh waste, evaporation occurs only in the upper part, only over a few centimeters, because then from deeper parts, water cannot come to the surface by capillary forces. It's not possible because the pores are too large. In MBT materials, we have small material size, we have small pores, we have a lot of water in the pores, and then therefore the evaporation rate is quite higher. So also here we have less leachate at the landfill base. Let's have a short look of typical values which had been determined on different test areas in Germany from different authors. You can see different sizes, up to 120 millimeters, so very coarse material, finer material, here very fine material, 8 millimeters only. And what you can see, this is a typical situation we have also for fresh waste. We have a big variety of values we can determine in our waste. This is to be expected because we have also in MBT, if you have a look at the micro scale, we have big differences because sometimes we have a little bit more of plastic or we have a lot of fine material. So this is why we have these differences. But what you can see here is this area, which is given here by the German regulation, MBT waste. We have lower permeabilities compared to fresh waste. In this case here, these investigations, they had quite high permeabilities because compaction has been poor. Here you can see sometimes, or you can find it also in literature, here small values below 10⁻10 meter per second. There you must be a little bit careful. You have to look how this value has been determined. Very often you take a sample at the landfill out of the waste in a cylinder, and you bring it to the lab, and then you make the investigation of the permeability. And what might happen if you take samples in this way, that if you have plastic inside, the orientation of the plastic is very often horizontal. And if you have larger parts, for example, here 100 millimeter, and your cylinder has a diameter of 10 or maybe 15 centimeter, then a large part of the cylinder is closed by this plastic material. And therefore, the permeability is low because through the plastic, no material is flowing. So the vertical permeability in waste is sometimes problematic. If you look at soil science, there usually you say the finer the material is, the lower or the smaller is here the value. If you have clay, you are here in the area of 10⁻10. If you have a gravel or sand, you are more in the area here 10⁻3, 10⁻4. This is not the case always for waste material, because we have these larger parts which have a big influence on the permeability. So the next point is with this low permeability, we have to be a little bit careful, especially after a heavy rainfall event, or also if we have a long-lasting drizzling rain event. So if it's very wet, then we might get some impoundment of surface water. And you can see some examples. So if you are walking here over the surface of your landfill, maybe here this low pressure, it's like a sponge, the water is squeezing out. Or here's this impoundments, you can see some openings on the surface completely filled with water, and then you can be sure you cannot drive anymore with your engines over the surface. And also here the compaction with such a smooth roller is not possible. It's looking nice, but if you have a closer look, you see that this nice smooth surface is completely destroyed. So we have this soaking, we have these problems with the traffic, and the compaction is not possible. So better wait a while when it's raining before you start placing some waste on the top of your landfill. So this is a problem. So how can we avoid it? Maybe we place here a temporary cover. When we know that the next day it will rain overnight, we place here a thin foil on the surface. We put some load on it so wind cannot blow it away. And then after the rainfall event, we can take it easily away again. But what might happen, the waste below the surface will be wet also because of condensates. The wet waste is wet, the surface here will be warmer on top, colder below the foil, and then we get this problem with condense. Then we get the same problems, trafficability, and maybe then the foil is slipping. So it is a solution, but not a very good one. It's much better to build up the surface with a certain slope. If you have this nice smooth surface, and when it's raining now, the water will flow because of gravity down from this area. So we don't have this impoundments. You need a certain slope, 15 to 25% should be enough. It shouldn't be too steep. So most of the water, when it's raining, especially after heavy rain, will occur as surface runoff. And as I said, avoid disposal during heavy rainfall events. So we are looking at the slope. We have seen we have some parameters which are influencing the stability of our landfill and therefore also the slope of the landfill. Now, if you look at conventional landfills, here you can see the slope very steep. You can build it up vertically, the slope, if you want. It will stay there over longer time and it will not collapse if it is well compacted. The reasons are the plastics, which are able to take up the tensile forces. So they are acting like an anchor, which is holding back here the slope. So the waste wants to go down, but here the waste, the plastic material, which is in most cases here inside very horizontally, it's able to take out these forces, and this is why the slope will not collapse. In the case of MBT, it's quite different. We are not able to build up such a steep slope. You see here 50, 60 degree. Here for MBT waste, it should be below 20 degree because we have taken out these fibers, this plastic material, 25 or nearly less than 5% of the mass are still plastic material. So better forget tensile strengths and make a calculation as you do for soil material. So this is why here the angle is much smoother. So this you have to take into account, which means also that because the slope is not here as strong as here, you can place a little bit less of waste on this area. Instead of building up here like this, you have to place it in this smoother way. But you have to take care about it. So now let's have a look at the emissions. We have just seen the problems we might have when we are looking at the surface when it's raining. So an important parameter is surface runoff. The question is how much of the precipitation occurs at surface runoff and how much is going into the waste. So it's depending on the rain intensity. For example, a heavy rainfall event, you get a lot of surface runoff. But if you have this drizzling rain, maybe if you look at the complete day, it's the same amount as this heavy rain, but it's taking you not only 1 hour for this volume, but maybe 10 hours. And then the same volume of rain may infiltrate into the waste and you don't get any surface runoff. It's also a question of compaction. Good compaction means always that you get some surface runoff. The degree of saturation of your waste material. If it has rained yesterday and now the next day it's raining again, then not all water can infiltrate into the waste and you might get surface runoff. And also question of the slope. The steeper the slope, the more you can have a surface runoff. If you look at fresh waste, standard landfill. Usually here from such a surface, you will not see a lot of surface runoff. You will get here some ponding of water. Some water will be on the surface, but it will not flow to the side, or not a lot. So depending on the waste, on the way it has been compacted, you might get 15 to 60%. You see this huge range of the precipitation you will get at the base of your landfill. So quite a lot of water, which might be at the base. So this high amount, for example, of leachate volume you have if you take a caterpillar for compaction, where the compaction is much lower than you make it with a compactor, then the leachate volume will also be reduced. So from operation also you can influence the amount of leachate, and this leachate has to be treated. And also from this surface, evaporation is quite low. Only the water which is here on the surface of a plastic material will evaporate when the sun is shining again, but from the resting material it's quite low also. To compare it with our nice surface, you can see, depending also on the slope, that around about 25 to 35% of the precipitation might be going to the side as surface runoff. Here's a test area in Germany. Somebody has made some monitoring, a slope of 1 to 2. So it's not too steep, but at a heavy rainfall, more than 60% of the rainfall was flowing on the surface and what was not going into the waste itself. So the leachate volume at the base is therefore also smaller, much smaller than here. When it's very well compacted, when you have a steep slope, you can expect about only 5% of leachate, of the precipitation. And from this surface, the evaporation will be much higher. It's not only 1 centimeter, maybe several centimeters. This waste material will dry out when the sun is coming out again. And then when it's raining again, this volume can be refilled with water. And it's not going in deeper parts, but it's stored nearby the surface. Some values, just you have an impression from a test area with a very small slope, only 5%. It has not been enough. The tests have been made just to get an impression what might happen. And you can see here nearly 3 years it has been monitored. And on a regular base, on one hand precipitation, and here what has been as surface, the volume of water at the surface, the green line, and the red line at the base of our test area. And you can see out of this data that both together, both values here, surface and base, leachate around about 65%. And in this case, here the distribution between surface and base leachate is 1 to 1. So the amount of surface runoff is low because here the slope has not been steep enough. So here we got some impoundments on the surface. You have had some problems always also, but later on it has been changed and then the surface runoff increased. But in the case you don't have MBT material, but you have only fresh material, then the red line would be much steeper. So maybe you will end here in this area only for the leachate at the base. So the leachate quantity is one point. Important for us are also the qualities of the leachate we are producing. So if you are looking at landfills and also at the emissions, you will find this type of graph very often. These are the different phases we have when we dispose waste on a landfill. So here we start with disposal, and here time. So this time we have different phases. In the beginning, we have this aerobic phase where we have some air inside the waste, but in a very short time it's getting acidic. Then we have the first production of methane, then the long-term steady methane phase, and at the end air from outside is coming again in our landfill. So here the length of this phase, they are not showing the reality. No? For example, the aerobic phase may occur only for 20 minutes, 30 minutes, while this steady methane phase may last 20 years, 30 years. But we have these different phases, and we have also different concentrations in leachate. If you look here, in the beginning, the biological process starts. In the acidic phase, we get very high concentrations of COD. And the longer it lasts, then the concentration is reducing. And the acidic phase, as the name is telling you, we get very low pH values. And this is important also for the dissolution of heavy metals. And we have here also some ammonia. As you see, in the beginning, we have a very high loaded leachate, and then with the time, it's getting less. And what is happening if we are now doing an MBT treatment? We are cutting out all these phases. We are starting here in the phase at the steady methane phase. So these high values of concentrations or these low values of pH, we don't see it anymore. So the concentration in leachate is quite different. Let's have a look at some values which had been determined at different landfills. So here also a test area, and we just wanted to have a look at the electrical conductivity, a parameter which can be determined very easily. And we have looked also at rainfall. So the electrical conductivity shows us how good and how fast some soluble components are flushed out by rainwater. And if you look here at the values, 20,000, 30,000 or more, you can see there is no difference to fresh waste. So by MBT, this amount of salts is not reduced. So it's nearly in the same order of magnitude. And what you can also see is that when it's raining here, when you have heavy rain, a lot of rainfall per day, then it's increasing. Also the amount of dissolved salt. So we have always both effect. If a lot of water is coming into the waste, then maybe a lot of substances are getting into solution. Or, on the other hand, the rainwater which is coming into the waste is diluting the concentration. So there is not always a relationship between the height of the concentration and the amount of water which is responsible for this leachate. So here we can see it's very similar to a normal landfill. But now let's have a look at COD, the organic compounds in leachate. Here we have on one hand the red line is the discharge at the base of our landfill, and the other one is the one at the surface at the runoff. And you see here at different times a new layer of waste has been placed. At last we have here the yellow line, which means this is the limit value. If you are below this line, then you don't have to purify your water. You can put it into the next river. You see, sometimes we are for a short time below this value, especially at the surface runoff. But here, after the placement of the new waste layer, we have a strong increase, and we were asking ourselves what has happened, and we make some tests with the material which has been placed there, and we have seen that the quality of treatment has not been very good. So this might happen that sometimes they have also problem in the MBT plant. We have higher values. But what you can see also at the base, we are here in a region of 1,000 to 2,000 milligram COD per liter. So if you compare it with the fresh waste, especially in the beginning, when we have this acidic phase, COD might be 20,000, 25,000. So here we start already at a much lower level. The next here is also an important parameter, the value between, or the ratio between BOD5 and COD, which is showing you how much the organics already had been degraded. And you see here the values are somewhere between 0.01 and maximum 0.12, which means this is water which is very well degraded. So we have still some organic substances inside, but the degradation by biological processes is very difficult. So this is the so-called hard COD, which takes a very long time to be degraded. So these values, if this ratio is below 0.15, this is the same quality you can also find in the landfill, which is 20, 30 years old. So you see, by this MBT treatment, the degradation is well working. So the load in leachate is quite low. The next parameter is ammonia, also a critical parameter for groundwater. Also here you can see this effect we have seen at COD, the strong increase. The same happened with ammonia. So the problems with the treatment itself. The concentrations here are going up and down, but they are always at the base, especially also here below 1,000 milligram per liter. And in the surface runoff, you see that here, mainly because of dilution, we are below the yellow line, which means you can directly discharge this water. So also here, the mean value here at the base, only 10 to 50% of the values for fresh waste. Last one, just a short look at heavy metal, in this case zinc. Why zinc? Zinc we have in very high concentrations in the waste for different reasons. It is one of the metals with the highest concentration, and zinc is also very mobile, so you can flush it very well with water. Here the same situation. Here's the value for discharge of wastewater, 2 milligram, and you can see that usually here we are below this limit. In this case, this also might happen if you are looking at the mechanical-biological treatment. For example, if you have a small battery, zinc-carbon battery, for example, and you have it in your waste, it is crushed, and then you have a lot of zinc inside. Or also if you have a lot of diapers, for example, in waste diapers, also you can find a lot of zinc. But it's always a short event, and then it's going down again. So there is no big difference between this MBT material and fresh waste. It's also not to be expected because MBT is not degrading the heavy metals. It's only the question if we can sort it out or not, and a small battery is very difficult to be sorted out. So let's have a look at typical values again. On one hand, for fresh waste in the acetic phase, in the beginning, where we have this strong concentration, that then the concentration in leachate in a normal landfill over longer time. And if you compare it with the values of MBT landfills, and you will see the difference between these two columns are not as high. But if you compare it with the first phase of the landfill, this acetic phase, before we get here into the stable mesogonic phase, may last 2 years, 3 years, depending on the conditions. And in this time, we have this very strong contamination of the leachate. And we are nearly always much below these values. So we get a much better quality in view of the leachate emissions. The question here in Europe, if you look at MBT, is then also how long does it take until we can get out of the aftercare phase. Aftercare phase is the last phase in the life of the landfill. We have the construction, we have the operation. After operation, the landfill is closed, but we have still some problems with gas emissions and leachate emissions. So we have to make the aftercare, we have to control it, we have to monitor it, we have to treat the emissions. And the question is, how long does it last, this aftercare phase? Here a look at the leachate emissions. And this has been calculated out of tests, of leaching tests, which had been made. So we assume a height of the landfill, 20 meter, and about 250 millimeter of precipitation are coming into the landfill. So here we are only looking at the effect of flushing, not the effect of biodegradation, but as we have seen in this old waste or also in MBT material, the biological processes are still present, but the activity is very, very low. Most of the substances are flushed out with water. So here for some parameters, here colleagues Stegmann from Hamburg, he has made a lot of investigation in this field of work, and you see they compared here standard landfill with the fresh waste and MBT landfill, and the starting concentration in this case is in the strong phase or in the static phase of methane production. Not interesting the first phase, but this phase where we have this long-term emissions, and compared it with MBT landfills. And you see the differences are not so very high here in view of the COD. Here is the target value. This is the value we have to reach in the end. If we are below this, value, then purification of the leachate is not necessary anymore. And out of this, you can calculate how much time it will take. And you will see, yes, it is a little bit lower in the case of MBT, but it takes also time. So with MBT, the techniques we are using in view of the material which can be flushed out, the effect is not as large. So this is why, for example, they are using this flushing reactor landfill. So they pump water inside to reduce very fast these concentrations, so that in the end it doesn't take such a long time. So here we have a little smaller values. Here for nitrogen it's better, but here for COD, for example, it takes a long time, because also these organic substances are very well adsorbed on the surface of the waste, and it's also difficult to flush them off this surface. Sorry, but I feel that I'm losing my voice, but I hope I will have it until the end. So just a short summary of all these data for the leachate. So we have to collect surface and runoff and leachate. We have to collect it. We have dilution effects, especially in the case of surface runoff. A treatment, we have to have a look at it, if it is necessary, always also for the surface water. Then we can also observe that sometimes we have a short time increase after the emplacement of new waste layers. So this is an effect which sometimes occurs. And the concentrations are much lower than in fresh waste, typical for landfills in the stable methane phase. And the biostability is quite high, which means our MBT has worked very well in view of this organic material. Closely connected to this degradation of the BOD and COD in leachate are the landfill gas emissions. Here is such a graph showing you over the time how much of the gas can be collected in the different phases. So here we have the disposal of waste on the landfill, and in this phase it is very difficult to collect the gas. Most of the gas is going into the atmosphere, so you see 30 to 40% can only be collected. Then we are stopping the operation. We do not place new waste on the landfill. We put a first cover system on it, and then the amount of gas which can be collected is increasing to 60–65%. And then we have here on the long term this final cover, which is really gas tight, more or less, and then around about 90–95% of the gas which is still produced can be collected. So you must take care. These 90% does not mean 90% of the total gas potential we have. Now, we know how much gas is produced out of 1 ton of waste. And this does not mean that 90% of this gas volume is then collected. It does mean that only the amount of gas of an, let me say, 15-year-old waste, which is still produced, 90% of this amount of gas can be collected. So it's much less. So you have to take a little bit care with these numbers. And then it's reduced because the degradation comes to an end. And at last, we have very small amounts of methane, which are still in the landfill body, but which can be extracted only with a large effort. And the same as we have seen for the leachate is also happening when we have MBT before. No? All these high amounts of gas emissions we can avoid if we do MBT. We start at this moment where we have this final cover. So where we have already only this very small concentration. This is the material which is going to the landfill. So we don't have these big amounts of landfill gas which is going into the atmosphere. So roundabout a reduction of about 80 to 90%. So only 10% of the total volume of gas which is produced can go into the atmosphere. So depending on the waste, type of waste, also we assume that 10 to 45 cubic meter per ton dry substance we still have as a potential in our MBT material. And we can expect that this gas is flowing very slowly through our landfill, MBT landfill, because we have seen the low permeability. It's also a low permeability for the gas and not only for the liquid. And also we have very low temperatures in MBT landfill. Temperature has an influence because if we have a gradient, when it is warm inside of the landfill and outside a little bit colder, then we have a good transport because of this difference in temperature. But in fresh waste, we have temperature 50, 60 degree, but not in an MBT landfill. There we maybe have 20, 30 degree, but not more. So we don't have this driver of the transport because of this temperature gradient. And also the gas production is much lower. So what can we do with this remaining gas potential? How can we treat it? We have different possibilities. On one hand, we can use an active system. For example, if we have already installed a system with gas collection shafts or a horizontal drainage system, we can use it also if the amount of gas is reduced. We have small volumes of gas, and also the gas concentration is reduced. The lower the gas concentration is, the higher the effort to treat these low amounts of landfill gas. So we have different possibilities. Thermal oxidation, which means in most cases a high temperature flare, down to 1 cubic meter per hour you can treat. Also low concentrations down to 5%. Sometimes, depending on the technique you are using, you need a secondary combustion, which means you have to add from outside some gas so you can really get this thermal oxidation, this burning of the gas. Or you can also use this non-catalytic thermal oxidation. There you can also use very low concentrations. If the concentrations in your gas are higher than these concentrations, then you have to dilute it. But it's a technique which is which has very high costs for installations, and sometimes has also some problems with other substances which might be in the landfill gas. So it's not used very often. So in these cases, usually you cannot produce some energy. We have here some equipment for thermal oxidation where you can produce a certain amount of electricity, but it's just enough here to use this energy here for the engines you have on place. So in this case, the main goal is to destroy our methane and not to make energy out of it. So these are the active treatment possibilities we have. There are a lot of developments in also at the moment in this area to get more techniques, or we use a complete other system. This is a passive system, which means we don't need any gas shafts or horizontal drainage systems. We can use the waste as it is on the landfill, and it is a passive system. We don't have to suck out the gas from the waste material, and we do it with a so-called methane oxidation layer. So this is what we have a closer look in the next minutes. Here, such a typical methane oxidation layer. Here, the material, we have a look what it is, a certain height you need. On top, you have a soil material, natural soil material with some vegetation. We have a gas distribution layer, and we have the landfill body where the gas is coming out uncontrolled. And we need these different layers for the functioning of our methane oxidation layer. So here we have some bacteria inside. They need here methane, they need oxygen, and then they can reduce it to CO2 and water and energy. So you need both. Only in this area they are also this methanotrophic bacteria. They only can live in this area. And this is then the reaction which is occurring in this small bacteria. And also important, they are already on place. You don't have to make an inoculation. You don't have to add them. They are in the soil or whatever you use. So this reaction is quite simple, but there are some points you have to look at. Is on hand the methane load. If too much methane is coming into this layer, then it will not work. It is too much for the bacteria. They cannot, this reaction cannot occur for all the methane which is flowing through the methane oxidation layer. Then also important, not only the load, the height of the load, but also the spatial evenness, which means if we have big differences in the concentration distribution inside the layer, we also get some problems that in some parts it's too high, in other parts it's quite low. And also very important is that we have enough oxygen which is coming from outside into our system. And then we also have to look at the conditions that the microbes feel well. So we need a certain temperature. If it is cold, then we always get a problem. They are not as active. Humidity, they need a certain amount of water, so they can act very well. Too much water is also a problem. We need some nutrients, pH value, and. So a lot of investigations has been made in the past how this system is functioning. And what you can see, if you look then in our methane oxidation layer, this is a part where the oxidation occurs, where our bacteria are living. And here in these different points, here's the surface. Here we are up to 1 meter below the surface. Some samples have been taken and the gas composition has been analyzed. And you see here methane from the waste, around about 45–50%. And it's slowly going to the surface. And at a certain point, you see that it is increasing. So the methane in this area is reacting, or the bacteria are taking this methane to produce carbon dioxide. And you see, on the other hand, here, oxygen in the atmosphere, we have around about 20%. And the deeper we are going inside, the lower the concentration of oxygen. So, and you see, if the oxygen concentration is near to zero, then no more degradation occurs. So we have here a certain layer where we have optimal conditions between the amount of methane. So we are now still in this profile of the soil, and we have seen here's the reduction of methane and also from oxygen, and you see this area where we have this high oxidation rate. It started slowly from the bottom, then we have an optimum. Then here by the top, the concentration of methane is already low, so that the oxidation rate is also decreasing. So mostly in the upper 60 centimeter. Also, if we say the layer should be 1 meter, 1 meter 20 high, to be sure that we have enough space here for the oxidation. It's depending on the soil type, how large is this layer where the oxidation occurs. One of the limiting factor is that for the oxygen, it's difficult to get in deeper layers. Oxygen only here is transported by diffusion. Diffusion is a slow process. So the same of this profile, we can also have a look if you here for a landfill. Different points in this landfill where we have made these investigations in different layers, 90 centimeters from the top and 40 and 20 centimeter. And here you can see very well from the colors. Red colors means we have quite high concentrations of methane. That in the lowest part here we have large area, we have high amounts of methane. In the middle, then 40 centimeter, you see already here in some parts all the methane has been oxidized. And in the upper part, 20 centimeter, we have only here a small area where we have still elevated methane concentrations. Maybe that this is a hotspot. We will have a look later on. A problem which might occur that some methane is coming to the surface. So that there are some problems with the methane oxidation. So let's have a look what is possible, what loads are possible. So let's have a look what we have. If you look at different ages of the landfill, how much gas is produced, especially methane. Here an old landfill, 10 years after it has been closed, we have still a huge amount of landfill gas coming to the surface. Here some bio-waste has been separated before the placement on the landfill. And here now the first 10 to 15 years, you see the effect of the separation of organic waste. It has been reduced then more by 50%. If you look at mechanical-biological treated waste, a strong reduction. Here has been made by our institute. The technique of mechanical biological treatment has not been so very good. It has been a combination of anaerobic treatment and aerobic treatment. So we have still a little bit higher values of methane flux. And at last year, an old dump, really an old dump, and still there we have some values. So we see the large range, and out of the experience we know that these high values here above 100 liter of methane per square meter and day are not possible to be treated in the methane oxidation layer. So we, depending how we build up this methane oxidation layer, we have values 12 to 96 liter of methane per square meter and day. So this must be monitored before we start building up such a layer, that the emissions are not too high. Then, if we know, okay, the load or the flux of methane can be treated by such a system, we have to look at first this very important part of the gas distribution layer. So if you look here, this is a waste surface. So in some parts, gas is coming out. It's really uncontrolled. And this is not a very nice situation if we want to have a good methane oxidation. This is why we have this layer, to get a better distribution of the methane here at the bottom of our oxidation layer. This is the oxidation layer, and if possible, a very regular flow of this methane into this layer. This is what we want to have. This is why we build up here this gas distribution layer. So if we do so, then the risk that such a hotspot, that some parts we have a strong flow of gas, is reduced to a minimum. And also important, this layer, when it is raining, water is slowly coming down, and it is important that this rainwater is transported fast to the site. And this is why we have here this drainage material. So we only use minerals having a stable structure, so that not with time this material is crushed. If you have a limestone, for example, it might be a problem. And also we need a high permeability in this material. It must be much larger than the permeability of the methane oxidation layer, so that we can get a good distribution of the gas in this area. And also here again, calcium carbonate, not too much, to get here high permeability, so no reaction are occurring in this GDL. In most cases, this is why we use coarse sand, gravel, 16 to 32 millimeters. So these are typical values also for standard landfills for drainage material. Or you can also use larger slags from incineration processes. Next element is then the methane oxidation layer itself. In many cases, it's a natural soil. And the function is that we have a very nice flux of oxygen from outside into this layer material. And we need also certain boundary conditions for the bacteria on the long term, so they feel well and they are very active. In many cases, we have two layers on the top. Humus containing layers, a natural soil material with vegetation. This is also made to avoid erosion processes if it is raining. And then we have this layer where the methane oxidation occurs, and in this area not too much organic material should be inside of the soil material. We have seen, O2 from the atmosphere is only because of diffusion, because we have this concentration gradient, 20% outside in the atmosphere, inside of the soil material at a certain depth it's near to 0%, and this is why from outside gas is transported into the soil. But this diffusion is also depending on the porosity. That's the most important parameter. We need some space where the gas can be transported. So we need a coarse material. If we have low amounts of silts, that's very nice. If we have clay, for example, then we have a big problems. So sand material, washed sand, for example, is very nice also to use here. Then we have to take care in view of the compaction. If we are driving with heavy engines over this area, the soil is compacted and the porosity is reduced. And then it's more difficult for the transport of oxygen into the soil material. And also water content. It will happen when we have a rainfall event that for a short time the pores are mostly filled with water because it is raining, but this water is slowly flowing downwards because of gravity. And after a while, we have again an open pore space where we have a certain amount of water, but we have enough space also for the gas. Here are some values of the material for the requirements. So we need a certain amount of pore space, also when it is compacted, or also when we have this certain water content, which is usually this field capacity. Field capacity is the amount of water which remains in the soil against gravity. So when it's raining, the pore space is filled, then it's drained, and remaining is this field capacity, about 40%. Same values, but it's right. So we need this air porosity, we need this field capacity, we need a soil with low sensibility to compaction, not a soft soil, for example. We need a certain pH value in the soil, so not too acid, for example. We need a certain amount of organic matter, a low amount, because if the amount of organic material is too high, maybe then this material is degraded by biological processes. And then we are changing the conditions in our soil material. If we have a stable organic material, for example, smaller wooden parts which are usually not degraded at fast, then the amount of organic material might be higher. Also, we must have a look if there are other contaminants inside, so heavy metals, organic substances, or whatever. So we have to make an analysis according to the local requirements for disposal of these materials, and they must fulfill these requirements. And at last, here there shouldn't be too much plastic material, metals inside, so don't use waste material. Or you make a good sieving. If you can use MBT or compost material to a certain amount, but this you should have also have to keep in mind. So what is possible? Here some results from practice. We have different compositions of the methane oxidation layer. We have on one hand here the oxidation layer itself, and we have the gas distribution layer. You see different components. Here in this case, that we don't have a gas distribution layer. Here, instead of a coarse material, they used here a loamy material, so more fine material. And you see here from different investigations, and they have looked at the emission reduction with a certain emission rate. So they have determined how much gas is coming to the surface, and then have seen how much is reduced if this gas is going through the methane oxidation layer. And what you can see in these cases, when we have methane oxidation layer with a certain quality, and we need this distribution layer. We have very high emissions reductions of more than 90%, nearly 100%. If we have this fine material for gas distribution, it's much reduced. Also here, we have here loamy materials, which might be a problem. They used here shredded tires. These were not the problem, but here in most this loamy material, we have problems with the gas distribution into the methane oxidation layer. You see, if it is built up in a good way, then we are able to reduce most of the methane. But we always need these two layers in minimum. So how can it be built in practice? If we have an old landfill, we can build up, for example, such a bio window. So on old landfill, we have here a soil cover on the top, and here we have such a system of waste, and we put here a gas collection and distribution layer in this area. And we open only a small part of this conventional landfill cover and put here our methane oxidation material inside. And maybe if it is a larger landfill and if we have much more gas, then we need not only one window, we can place several windows. So we have here small emissions, which are about the limits, the allowed limits. And then by itself, the gas now is going into the gas distribution layer, and here occurs the methane oxidation. So this technique is used quite often if we have an old dump, which is already covered, and we want to extract the remaining gas. Or what we can also use is the same, nearly very similar. Now we have replaced the cover completely by this bio cover, by our methane oxidation layer. Also here we have the gas distribution layer. The amount of gas is low, and also the concentrations are low, so that an active degassing is not working anymore, but the emissions are too high and they are not allowed. So here now we have the complete surface. So if you compare it with the bio window, here the emission potential of this waste is higher. So we need a larger surface for the oxidation of the complete methane inside of the waste. At last, one is here the biofilter. So you can use it if you have a gas collection system in your old dump, some pipes, some drainage, and this you can connect to a biofilter. So a small part of the cover is opened, and such a biofilter system is installed and is connected here to the gas pipes or to the drainage pipes. Gas is flowing here inside. Usually we have a lot of water vapor in the gas, so we have to collect this water, which will condensate here at the base, and then the gas is flowing through this part. So this is working also quite well. We have also here good experiences. Here are some pictures how it is built up. Here's a construction of such an area. Here you can see the gravel material. So this is a gas distribution layer. And now here's some composed material mixed with soil is placed in this area. So it is a window. In this case, here after a while you see there are some plants on the surface, but it's working quite well. And after a long time you cannot see that there has been here the methane oxidation layer, but it is still working. But what might happen, and this nearly happens always, is that we get some hotspots. So you have to monitor the system. every year you make some measurements on the surface, and what you might see after a while are these hotspots. So this is a quite small area, 1 square meter, 1 to 1 meter, and you see a lot of measurements have been made in this area. And in very small areas, you have here very, very high concentration of methane. Small parts only with high concentration in the remain area, there the methane oxidation is working quite well. And if you look then, if you open the soil in this area, you will see such a channeling. Here the black area is showing you that the methane is in this area in higher concentrations. We have anaerobic conditions. And here we have some fissures here inside, some openings, and the gas can flow very easily to the surface. So here also this black color, and if you are taking here a sample on the top, you will get this high concentrations, these high peaks. And so this you cannot avoid. And if you look at these profiles, this is on the side nearby the hotspot. Here you can see this high concentration of methane, which is reduced, and also the oxygen, which is here reduced also. And at the hotspots, it is looking quite differently. Here we have from the bottom to the top nearly the same concentration of methane and also carbon dioxide in high concentration. So in this area, it is not working. So this is why you have to make monitoring. And if you see such a hotspot, you have to open your system to replace the soil material, and then you can hope that it will work better in future. So the performance of methane oxidation is very good, as you can see. So here is the emission potential. If you have fresh waste, round about 200 liter per ton. So it's depending on the composition as always, but here a mean value of 200 liter per ton. By MBT, we are reducing this big amount to about 40 liter per ton. And if we place this material below such a methane oxidation layer and make a measurement on the top, then maybe we get 4 liter per ton of remaining gas potential. So this is very, very low. It might be reduced even, so it's depending also on the methane oxidation layer. So you see the big difference we have between the fresh waste and if we make MBT and we use such a methane oxidation layer. So we can do a lot in view of the greenhouse gas emissions by this somehow not so very cost-intensive and complicated techniques. So let's have a look at the long-term performance. So maybe it's just working for 1 year and afterwards maybe there are some problems, but we have in the meantime, especially in Denmark, they started very early with these methane oxidation layers. They have a lot of experiences also over longer time. So you have to monitor it. As I said, you have to make every year at least one time surface measurement with FID, this detector. With this detector, you can only see if there is methane or not and the concentration, but you cannot determine the flux. Only the amount of methane in the air can be determined. So on the surface, you should also have a look in the methane oxidation layer itself, to have a look at temperature and maybe also take some samples to analyze the gas concentration. And then from these data, from these profiles, you're now determining, you can also see where is the methane degradation area. So maybe that after a while, this area of methane oxidation is getting smaller and smaller and is nearby the top of your layer. Then it shows you that you have a problem with the diffusion of oxygen into the methane oxidation layer. So then you might change your material. And also the material of the methane oxidation layer should be analyzed from time to time, 5 to 10 years, to see if there is a strong mineralization. Have a look at TOC, biological activity also. Have a look at the nutrient. Maybe you have to add some nutrients. And also to have a look at the porosity, the density of the material, and the air-filled volume. So the effort for control is not as high. And here you can see what might happen on the long term. This is an example from Denmark. Here they made the investigation to have a look if it is working or not. They started before putting the biocover on the top of the landfill. Here in April 2010, they have placed the biocover, and it takes always a certain time. If you place the biocover on the top of your waste material, then it takes you several months until it is working very well. So the system has to adapt to the gas concentration, and then it's working after a while. You see in the beginning we have a little bit higher concentration, but then they are reduced to a certain amount. So this is around about 2 years later. Then they have stopped to monitor the system. And 4 years later, so now we have here 6 years after we have started to place it, we have still low concentrations. They are increasing a little bit, but they are still very good methane oxidation rate. So after this 7 years, it is working quite well. And this has been the summary of the investigators. So still low emissions, that they show the profiles they have determined that they still have oxidation in the methane oxidation layer. Oxygen is still diffusion inside of this layer. They have elevated temperatures. They show also that it is working well. And they have made some tests of the soil materials they've placed in the biofilter. And they are showing that compared to the values at the beginning, it is working quite well. And they still have problems with hotspots. So this is a problem which will always occur, that you at a certain place some more gas is coming out. It will change. It will not be always at the same place. It might change over this large area. So in total, the biocover is still working. So in the last 2 hours, I've told you a lot. So let me just make a short summary. So if you want to use MBT, then you must always think of what to do with the material which is remaining after MBT. And this material you have to analyze to a certain amount because every technique has an influence on the quality and on the behavior of the material which is going to landfill. So it is not possible if you have a landfill and an MBT in the neighborhood and you want to build up your own system to say, okay, these are the values I can take from the other landfill or other MBT. It will not work. So you have to make some investigations in the beginning. And then We have some changes. We have other engines, as we have seen. We need less infrastructure. For example, no landfill gas collection system. We have a longer lifespan of the landfill, so we can place for a longer time. We can place waste on the landfill. We need less staff also for the operation. And also important, we don't have any more birds, rats, and other animals on the landfill. In view of the water household, we had lower volume at the base. We have lower concentration in this leachate. We need to treat this leachate on the long term also, but with other techniques as we have now for fresh waste. And also we have to collect surface runoffs, we have to control it, and maybe that in the beginning we have to treat also this surface runoff. Then, in view of stability, we have this higher density of the material, we have low settlement compared to fresh waste, but we have this flat slopes we have to take care of, and also this higher risk of poor water pressure, which might occur inside of the landfill, which reduces the stability of the landfill. In view of the gas, we have low volumes and concentration of methane in landfill gas. We have still to treat this low emission rate, this low fluxes, but we can use this very simple passive system, which has low costs, invest costs, but also during operation. And at last, in view of aftercare, aftercare will still be necessary. In view of the duration, it's difficult to say if it is really shorter than with a normal landfill, but the monitoring effort is much lower, because we don't have this high emissions in view of leachate and also of gas. We don't have this high settlements, which might make some changes in the top cover system on the long term. So it's much easier to handle so that the costs also of aftercare will be lower. So in total, let me say that MBT is a good chance to use landfills on the long term, but you have to keep in mind MBT will not work, I think, for megacities where you have 5,000, 6,000 tons of waste which have to be treated every day. But for smaller communities, I think it's a very good alternative to incineration. So let me say thank you for your attention. It has taken a little bit longer as I've expected, but that's always the case.